Hello everyone. Good evening. Good evening and welcome to day 5 of our natural language processing masterclass. And in this session we are going to continue with the pre-processing methods. In the previous session we have completed some pre-processing method. So starting with tokenization, where we have done or converted our corpus or our text into tokens. We have turned them into sentence wise tokens or word wise tokens. So mostly we prefer for word tokenization because we'll be collecting all the individual words and then working in it. So continuing with that, after you convert it into tokens, what is the process we are going to do and how to turn it into numbers? That's what we'll be seeing in this particular session. So starting that on day 5, text pre-processing, stop words. So the first content we are going to discuss in this session is called as stop words. So what is stop words? As the name itself suggesting, we are going to stop these words. So what are these? Stop words are words that occur frequently in a language and they do not carry much meaning on their own, such as the, yeah, and so on. So we have a lot of stop words, a collection of it for each language. It differ, and for English especially we have it. And stop words are often removed. Why? Because during the pre-processing, to reduce the amount of noise and focus more important words in the text, and these words are available in NLTK stop words and they can be used to remove in our data set. So we will be using the library like what we used for sentence or word tokenized from NLTK. The same library we are going to utilize for this particular task as well. So these are some of the examples of stop words. We have I, me, my, myself, we, are. So we have a lot or bunch of them. So let us go and see what all stop words we have. So we can actually import from nltk.corpus. We can import stop words, and with the help of this we can actually work with it. So let us go into our Google Colab and I have some sample sentences here. Let me run this. So I have a sample and I have something known as data, so which we will be using later. First we are going to be interested in something known as sample. So first let us see what we have in the sample text. So it's a paragraph. Okay, so we have a paragraph. It seems like something about blue whales. It seems like it's a basketball game and a team name, and we have some content about it. We are not interested in the content, we are interested in processing this. So before taking that, we will import from nltk.corpus. Let us import stop words. So in this stop word, what you can do is you can call stop words dot words, and you can pass like the language. So we are interested in English, right? So if you run this, you will be getting that. And yeah, as we have discussed earlier in our previous session as well, so we will be required to download some things. So for now we'll just run and download the stop words, and later on when we go into the content we'll start running all, so that it will download all. It will take its time, but still it will be downloading all. So once we move into the content theory parts, we will do that. So first I'll import nltk, and then we can go for nltk.download. First we'll just download this alone, stop words alone. So whenever you use, please make sure you do it so you can use it without any issues. So what do we have here? We have a bunch of stop words available. It is a list, and you can actually check the length of it as well. So we can store it in stop underscore words is equal to nltk. Okay, it is, we have already imported to stop words dot words of English. So with this, let us first check the length of the stop words. How many stop words we have? 179 stop words is available in NLTK, and for this NLP process there are other libraries as well, which is Alternative, which if you are interested you can use that. So the final process we are going to do is same, tool changes. Okay, but the final thing which we are going to achieve is going to be the same in both. And here especially when we try to remove stop words, we can also remove any punctuation. So we know that we have some punctuations available, right? Maybe if you look at your data, which is, I hope it is called a sample, right? So the earlier sample we were discussing, so this has punctuation marks as well. So if you are not interested in punctuation, we can pre-process that as well. We are just considering the words for now. So we can actually import string, the inbuilt module of Python. And if you go and call string.punctuation, you will be getting all the punctuations which is available, all the characters. So we can simply store this. We can just create a variable called as punctuation, and let us store this. And with these things, what we can do is before continuing, we need them in tokenized format. The word should be tokenized. So let us go and call nltk dot word underscore tokenize, and we will be passing our sample inside. So we will be getting a list. Okay, it's first we'll download this, later on we'll go with download all. That's a better way. So for now we'll download this, and we'll see the sample. So we have tokenized the word, right? So yeah, so this is our tokenized. So I'll just go with words is equal to, I'm storing it. So what I'm going to do is I'm going to just iterate through it. Every word in my sentence I'm going to iterate through it, and then what I'll do is I'll check whether it is a punctuation or a stop word. If any one of that clicks, okay, we are going to remove that, okay. Or if a word which is not present in both punctuation as well as stop word, then it's an important word which we need. So we will be storing that. So I'll create a new list, new equal to a new list, and what we are going to do is we can just go and utilize for loop for x in words. So the words are our data, right? We have tokenized them into words. From that, every word is taken. So if x not in stop, okay, so if your word is not in your stop words, okay, then this will return true. At the same time, I will be using AND operator and check another condition here, x not in punctuation. So if both are giving true, then that means the word you got is not a stop word as well as it's not a punctuation. So we can go with new dot append, and we can pass the particular word x. And now if you look at x, you will be having a list of words. Okay, this is not what we expected. For x in words, first let us check the words now. Okay, we have everything, and we have our stop words as well. And I think this AND operator is not working properly. We can just enclose this in the bracket. So finally it will check whether both are true, and then it will proceed further. So when we run this and check our, okay, the problem is till now I am trying to print this x, but I need to check the new, right? So the last entry is a full stop. That's why we got that issue. It's my mistake. So we have this new variable. So that's what we should check. And what we have here is the new words, or the words which will be removed based on stop words and punctuation. If it is not in there, this both going to return true, and we get that. And if you want, you can look at the length of this. So now after this processing, the word count is 81. But if you look at your words which you had earlier in your sample, it is 156. So nearly you have reduced the noise into half by taking only the important things and neglecting other words. So if you want to combine this, okay, so this is fine. We will be using them as word tokens. But in any place, if you want to combine them, what you can do is you can use, if you have a list, you want to combine them into a string, you can create an empty string like this with some spaces, and then you can use dot join, and you can pass your sentence words list of words here. So every word is now separated with a space, and then it will be joined. So this is what after processing. After removal of stop words and punctuations, if you look at your sample, this is what your sample looked like. Okay, so some of the word just has been removed, there has been removed. You can see some of these persist, some of these has been removed, and that is a removal of stop words. So after stop words removal, we have our list which is new, which has all the words which is important. So that is the use of stop words, and we use punctuation as well. If you want to convert this masterclass into 1 month certified internship on natural language processing, you can join as an internship user, and you will be getting 30 days of recorded sessions, 30 days of PPTs for download, all the downloadables of every 30-day content, 10 plus source code of project files, 1 month internship certificate, participation certificate, 90 days of access to all the courses, 4 hackathon live session and community group. And you can get all these things at a discounted fee at 799, and the registration link is posted in chat box. You can join as an internship user and get all these benefits of 1 month internship. You will be getting 30 days different day wise plan, starting from the basics of machine learning with their project, and then the NLP continuation as well. So you can get all these things at a discounted fee at 799. The registration link is posted in chat box. And if you want to register for our 4-in-1 bundle offer, today is going to be the last date. So you can get Python with machine learning, with NLP, with generative AI, 4 different internship. So you can get or learn from the scratch. It is 4-in-1 bundle offer. The registration fee for it is 1299. The offer ends today. Today is the last date for it, and the registration link is available in chat box. It's a limited offer, and this is going to be the last date. So if you get this, you will be getting 4 different certificates, 120 records, weekly live session, 30 plus projects, downloadable PPTs, internship confirmation letter, 1 year validity for using this, and community support. It's a self-paced course. You can watch at any time, and today is going to be the last day for availing this. So you can register for this 4-in-1 bundle offer by clicking at the link which is posted in chat box. To ignore that and all. So this is one way of pre-processing, so which we prefer for stop words. And especially there is some thing which we also keep in mind, that when we go with stop words, sometimes it can remove some of the stop word. There are some stop words or some words which can carry some information, and accidentally if the stop words has removed it, then we will be actually losing the information. So it is suggested to start with stop word, and if you find a situation where your model is not performing well, you have no idea about where the leakage might happen, you can negate the stop word or remove this process of stop word and proceed without that to see whether there is an improvement or not. But it is suggested to remove the stop words when we move towards the projects. So moving into the next pre-processing, we are going to discuss about stemming. So stemming is another important process, but we won't prefer stemming much. Stemming is the base thing, and then we have something known as lemmatization next. So we'll be going with any one of this, not with both. First we'll see about stemming. So stemming is the process of reducing a word to its base or root form, which allows different variations of a word to be treated as a same word. So why do we do this? Once again, we are trying to reduce the complexity of our sentences or our words. For example, the stem word of running, runner and runs is actually run. So stem is the base word or root word. You are going to predict that. In English, we have this tenses. We have other stuffs, right? The suffixes like running, runner, runs, studying, studied and all. So this we are trying to reduce to its base form. And stemming, actually what it does is, if you have some words like this, it is trained on this process so that it removes the suffix. Okay, so the stemming knows that it need to remove the suffix like ing or er or s. It is going to just cut it off. But the stemming don't know whether the resulted word after cutting off, you will be having the remaining word right in the beginning. It don't know that whether it is a proper word or not, or a perfect real word or not. For example, stemming is actually not always perfect. and it can sometimes result in the stem of a word that is not a real word or is not the correct stem as well. For example, the stem word of was will be wa, which is not even a real word. Also, you can see we will be getting some problems like this. If you look at the stemmed word of study, it will be studi. Again, studied will also be turned into that. So that y is turned into I, and in studied the same. Studies is also es is removed. So it just know it has to cut off the suffixes, but it don't know what meaning the resulted word is going to be. So it don't know that process and all. So it just cut it off and give you. So that is stemming, and we don't mostly prefer this, but let us see how to imply as well. So this you can take from your nltk.stem. You can import porta stemma, and with the help of this we can actually stemmatize a word or stem a word and get the resulted word. Next we'll see lemmatization. Before that we'll just imply the stemming part. So we'll go into our Google Colab once again, and this is fine. And for example, we can go and import first from nltk.stem. Let us import from nltk.stem, import porta stemma. So stemmer is equal to, I'll create an object porta stemmer. So it's better to go with the object. And first let us do it manually. Stemmer, you have the option of stem, and let us pass a word called as running. You get the word run. So if you pass inside stem is a command for stemmatizing, and if you want to like turn them into a stemmed word, what we'll do is we'll just call stem and pass the word inside. So for running it looks fine, it looks great. We'll do it for was. You will be turned into wa, which is not a real word. And if you look at studying, you get study with I, or study, the word itself you get study. This is not what we prefer anyway. So instead you can also look at this. Maybe we'll first do it. So we have our stemmer now, right? So stemmed words is equal to empty list, and I'm going to use for t in. Maybe we call our for n and new. Okay, we will pass stemmed words dot append. We are going to add it in the end, and what we are going to do is we can call stemmer dot stem, and let me pass the word n inside. So after running, if you look at the stemmed words, you will be having the words which are stemmed. Maybe if you look at the joined word, you can understand. So we'll join it into a sentence and see this. So you can see played. I hope it was played earlier. If you look at the base, maybe if you look at the sample, we can understand it. So the blue whale played has been turned into play. First, baseball. You can see baseball is not a real word here. L is missing there. Believe is changed. Excite is excited is changed. It just cut it off. It don't know that semantic meaning here. So that's why we prefer the ultimate next step, which is the lemmatization, which is better than this. Okay. So this problem was like stemming was the earlier version. The idea wise it was good. You are reducing the complexity, but the achievement was bad, right? Anyway, it's half. You can get some words good, some word was not good. But if you go with lemmatization, lemmatization is the process of reducing a word to its base form, which is called here as lemma. That's a stemmed word. Here it's lemma. And lemma is actually going to be a full word. So the lemmatization is similar to stemming, especially, but it produces a valid base form of the word that is found in a dictionary. So which is a real word it is going to give you. So the output of lemmatization is a word's base form or lemma, which can be a real word or a root form of a word. Here you can, if you pass this after lemmatization, you may get an entire word, a word which is complete, a word which is not something like a not available word and all. So we can use the lemmatizer from NLTK. We can go and use stem, and we can import the WordNet Lemmatizer and we can do this process. So for doing this, we'll go into our collab and let us continue now. So what we are going to do now is first let us import it. So from nltk.stem we will import WordNet Lemmatizer and we'll create an object Lemmatizer is equal to WordNet Lemmatizer. So we can call Lemmatizer. Here it is Lemmatize. Okay. So the function to convert is Lemmatize. So if you pass studying, you get study. Okay, we have to download it. So I think it's better now to wait or just run this command, which is download all, which we should have done earlier. So we will go with nltk.download all, and in between we'll discuss at the same time. So you can pass this all. Actually it will take some time, that's why I have negated to do it later. Anyway, we forgot it. Some of these things should be downloaded, that's the difficulty of nltk. But what you can do is whenever you start your collab, if you just go with import nltk and then call download all, so it is going to download everything and we can just go smoothly without getting any error. These are not errors, these are missing packages or missing things which once everything got downloaded. So instead of going one by one, so if we install this, then later on in the next process we will get other issue. So it's better to do it in a single step, and yeah, so it will be completed soon. So these are some processing. So if you look into it, first we had a set of paragraph. Your data will also, it is completed. See here, your data will also be something like a paragraph. So you turn them into tokens or word tokens, whatever you call it, single individual entity. You then remove the stop words, pick the important words alone, or then we can go for lemmatization. Especially stemming, we have this issue of not a complete word, right? So we can go for lemmatization, and first let us run this. Now it will be fine, we won't be getting error. So this is giving us studying itself. Maybe if you look at study, eating. Okay, so this is not exactly converting it though, right? Maybe first we'll imply this and see, maybe in the larger complex text it is going to perform. So let us go with for, okay, we have done it earlier, right? So for stemming, we'll do the same thing for here as well. Let us go for doing the same thing here with lemmatized word, lemma words, and we are going to pass it to our lemmatizer, and this should be lemmatized. Yeah, so now if you look at the lemma words, we'll join and see it. Okay, is there any difference? Let us see with dot join our words, which we have used it as a raw material here for running. Okay, new, right? So new is the after stop words removal, we had that. Wales played first baseball game. And regarding lemmatizer, the problem will come this way, especially like this will come especially in a scenario where actually we need to understand how this lemmatizer work. Earlier we have done stemming, which actually cuts off it, right? So the cuts off it, it will cut off the second half or the suffix and all. But looking into the lemmatizer, it will lemmatize considering the word, and it tries to lemmatize it, and it will understand or take in or treat the word, whatever it get, it is going to treat the word as noun. So if you know what is a noun or pronoun, we have adverb, verb and all, right? So it is also called as parts of speech. So that is involved here, and by default your lemmatizer is going to lemmatize the word thinking that it is going to be a noun. For example, if you try to lemmatize a word, let me do something like, we call our lemmatizer to lemmatize something known as runs or rocks. okay, you will get rock, so that is removed here. Especially if you have some other different word, for example, if we try to do something like, let us do it for the lemmatizer dot lemmatize. If you try to do it for running, we get something like running itself, because it is treating that as a noun. But if you pass it as a verb, you will be getting a run here, so we may need to fine tune in that way as well for our process here. And if you ask me, how should I know what it is? Maybe you are weak in English. You don't know what is, maybe for example, whether running is a verb, or rocks is a noun or a pronoun, or what should it be. I don't know what it should be considered. So what we can do is we can actually use our NLTK, and we can call for parts of speech underscore tag. Okay, so you can pass a word. For example, let us pass something like car, and let us get what we are getting. Okay, so we need to pass it as a list of string, or we can pass our words. You can see it is giving you NN, which is actually noun. And you can check for some other word. For example, let us do it for fruits. Okay, so let us give a name, for example, Elon. Okay, and then for example, he. Okay, it's a pronoun, so like that we will be getting. So how can I integrate it here, because we can't manually do this, right? So for that, what we can do is we can create a function in Python. Let us go for NLTK, like tag finding, and since we have, you will be getting this as not in a short form, not an enhanced form. So this will get the tag, so you can just get the tag. And what we can do is, if our NLTK dot okay, NLTK underscore tag, right, if it starts with like, you may get J, which is for like return. We can just go with, yeah, we will also import this word nut. So from NLTK dot corpus, let us first import the word nut as well, and from this we can get, okay, so word nut dot adjective. If it's J, that's what it is, so we can pass that. Or elif, your NLTK underscore tag starts with something like, let us have some other word, for example, V. So if it starts with V, then we can return wordnet dot, it is a verb, so we can pass that. Elif NLTK, okay, here I made a mistake, this is NLTK. So NLTK underscore tag dot starts with, we have noun, and if you have that, just return wordnet dot noun. And elif NLTK underscore tag dot starts with, let us pass R, so it is for adverb, so we will return wordnet dot adverb. Or else I'll just pass return none. Fine. So this is a function which is for conversion. So now how are we going to integrate this? So first we'll do some function which is called as define lemmatize sentence or words, lemmatize underscore, and we'll first get maybe we can do it for word. So lemmatize underscore word, get all the word inside. So once you got it, you can get the tag NLTK tag is equal to NLTK. We know if you pass post tag, and if you pass the word inside, you will be getting the tag of it. So from that tag we want to get map, right? So we need to get it back, and you know that this will return a tuple like we got here. So it is inside of the 0th index, inside of that first index, so we need to take it. Okay, so for that we'll write a lambda function simply. So wordnet tag is equal to, so we will go and just map it. by calling a lambda function of x, and this will be getting x of 0 comma nltk. What's the function name we had? Tag finding, right? So in that we will be passing our x of 1. So that will do the task, and then finally here we'll pass the nltk comma, okay, nltk underscore tag. That's what we will be expecting. And first we'll try to do it. So if you pass lemmatize underscore word, let us try to pass for a word known as running. Okay, we are not returning or printing anything, right? So first we'll print wordnet underscore tag. Okay, we are getting, since we are mapping it, maybe if you do it a raw version, you will be getting it. Okay, running, and it belongs to VBG. Okay, so it starts with this, so we return verb. So that's what we are trying to map now. Anyway, so we'll map it, and then simply what we can do is we can also do the lemmatization here. So I'll create something known as lemmatized underscore sentence or word. Okay, why to do many steps? I think we can simply do for the entire corpus. So here when we get a word, instead of we can do it as lemmatized corpus, and what we are going to do is here we get the entire paragraph, or let the name be word, but okay, words or something like that. We can go and turn this anyway using nltk dot word underscore tokenize. So we pass the entire thing. We'll do it here itself. Why to pass many things? So it will be now turned, and now we can imply. So we can start with for, since we have mapped it. So for word comma tag in wordnet underscore tag, what we can do is we can check if tag is none, then we can simply just call the lemmatized, okay, here lemmatized words, right? Lemmatized words, we can call append that word if it is none. Okay, lemmatized, yeah. So else we know that it has a tag, so we can ask it to lemmatize based on it. So it will be done lemmatized underscore words dot append. We can call the lemmatizer dot lemmatize, and we will pass the word and its tag especially. So this will be done. So finally when I try to return, okay, so once everything is completed, let us return this dot join and return my lemmatized underscore words. And now if you just pass your entire thing, maybe if you try with lemmatize corpus, and let us try with our, what do we have earlier? Do we have a sentence? I hope it's dot join our new, and if you do it, it has now turned it. You can see the difference, especially here what we had, it was as such. When you just do it rawly, okay, it need to understand what is the part of speech as well. So we create automation for it, and whatever we get, we are trying to map it as well. So this is what after lemmatized, this is what the result is going to be. And you can see it has been cut shorted. At the same time, the words are completely available in a dictionary, not a word which is not even a real word. And that is about lemmatization. So this is the difference between stemming and lemmatization. You know, stemming is easy, but it will return a word which is not even a real word. But when you go into the lemmatization, we will be, if you use these parts of speech as well, especially, it is going to give you nice results which we expect. So that is difference between stemming and lemmatization. And now moving into the next steps. So this is the process actually. So if you have a word, what you have done, you turn them into tokens, then you have removed the stop words, punctuations, then you try to lemmatize or stem your word. Don't do both of that. Do any one of that, either stemming or lemmatization. So after that, now we are going into turning them into numbers. Okay, so we are going to convert the pre-processing. These are basic versions. We will be discussing about bag of words and TF-IDF. These are basics. And there are some advanced versions, so that we will be discussing. We need to know the logics of deep learning as well for that. So we will be discussing in the future. So for here we discuss the basics. With that we can do a machine learning project, and then we go into deep learning where we will be implying that. So moving into that, we are going to discuss about bag of words. So what does this bag of words is? As the name itself suggesting, a bag of words is a representation of text that describes the occurrence of word within a document. Okay, so it is going to tell you the occurrence of words within the document, and we just keep track of word count, disregarding the grammatical details and the word order as well. What does that mean? It is called a bag of words because any information about the order or structure of the words in the document is disregarded. So you are just going to, maybe if you are collecting all the words in your sentence, you are just picking the word and putting into a bag. That's what we are doing here. So the model is not only concerned with whether known words occur in the document or not, not where in the document. It is not going to consider where you have in the document. So that is bag of words. It's one of the basic form. For example, let us see an example. Maybe you have three sentences. This movie is very scary and long. This movie is not scary and is slow. This movie is spooky and good. So we have three reviews from for a movie from three persons. You have three sentences. If you use bag of words, this is what will happen. First, it is going to take all the unique words in your entire sentences, entire reviews. You have this movie is very scary and long, and in the second sentence, don't take the repetitive words. You have not, and here you have a new word called as spooky and good. So if you look at that, you are arranging the words. Okay, and what you are doing is you are counting in your first sentence whether you have that occurrence or not, and how many times. See here, this occurred one time, movie occurred once, so you are counting that, and if it's zero, it tells that in this sentence we don't have that word. Similarly, if you look at the review 2 is occurred two times, so you have it 2. Okay, so you have that count as well. So you are also collecting the length of review in words. Finally, you can see here in 3 also we are counting this. This process is called as bag of words. It looks simple, right? So it is one of the basic step. It's like encoding, okay, where we are encoding the entire document. So if you have bunch of sentences, this is what will happen. If you perform bag of words, we will be implying that anyway now. And looking into bag of words, your output will be a vector like this. Okay, so which tells that 1 and 0 or any number which tells that how many times it present based on bag of words counting. Okay, but the problem is like before going into the issues and all, from sklearn.feature extraction.text. So this bag of words is from sklearn, from the machine learning library sklearn. So you can install and take it from feature select extraction.text. You can import the count vectorizer, which will do the process. But the problem with bag of words is there are some limitations. We'll see that and we imply it now. No word order. It doesn't care about which order the words missing out or how the words work together. For example, the second person has given that this movie is not scary. Okay, here I'll do another change here. This movie is scary and is not slow. Maybe if I took this not and placed it here, what will happen? Actually, this person is telling that the movie is not a scary movie and it is actually a slow movie. But if you pick this not and keep it here, the review changes into the movie is scary and it is not slow, which is fast, which is actually completely opposite, right? The words and the combinations has meaning, but this bag of words is not going to consider that. It is just going to pick the words. It doesn't going to understand that anyway. As well as it ignore context. Okay, so you don't know what context, what they mean and all. It just represent how many times they occur, and always same length, and it always represent text in the same length, which can be limited for different types of text and lots of words. It need to know every word in a language, which can be a huge list to handle, and it doesn't understand meanings. Okay, how often they appear, they don't know, they don't understand. You are not passing meaningful representation here, you are just trying to represent one of the basic question. And one more important issue is they can't understand one more thing. Okay, so if you look at your text, and what do we have here? We have some words. Later you are going to make prediction. Now you are going to enter a new word which is not in this particular bag of words. Then what will your model tell us? It will give everywhere zero. That word is won't even consider because it is a out of context word. If you have it, it is not going to take that into account. That's a problem that we may face. So that is one of the issue with bag of words, and it's a basic version. People use it for machine learning projects. So from sklearn underscore feature extraction, you can use text. In that we can import count vectorizer. So going into our Golab, and let us start writing the code. So first from sklearn dot feature underscore extraction, let us dot text as well. So that is for tabular, text is for text data. You can use count vectorizer and import. I missed import. Yeah, and bag of words is equal to count vectorizer. Fine. So let us do one sample on hands-on itself. So I'll call bag of words. You have the option of fit and then transform if you want to transform later on, or you can do fit and transform together. First we'll do with fit, which is learning part. So I'm going to pass a set of sentence here. Hello everyone, this movie is not good. Okay, so you have fitted now. So you can go and call bag of words dot vocabulary underscore. These are some options. If you go with vocabulary underscore, you get the vocabulary, what all words you have, and this number represents its order. Okay, don't worry about that. For example, first let me do this. If you go with bag of words dot transform, I'll pass a empty string here. So you get it as a sparse matrix. So you have to use 2 array. So you can see what I'm getting is I'm getting a total length of 7. I hope so, because your corpus has 7 words. 0, 1, 2, 3, 4, 5, 6. We have comma as well. And they have given the name as well. See here, 0, 1, 2, 3, 4, 5, 6. Their count as well. So this is what it represented, this place. 0th index is for everyone. So if you have everyone in your sentence, okay, if you transform everyone, you will get 1 there. Remaining will be 0 because you don't have good or not and all. Maybe if you have everyone good, so they are mismatched order, but you can see if you have good, that's first index, you get 1 here, remaining thing is 0. If you give a new word which is out of context, maybe car, which is not even here, you get completely zeros here. So that's how your bag of words actually work, and they have some limitations as well. Okay, so like for example, practically what we do is we fit our data here. Maybe if you want to transform, you can also do it. So fit underscore transform, it will turn that into your data into matrix transform. Okay, so you can check 2 array. So this is the entire representation. Maybe if you have some other words, for example, hello guys, such a great movie. Okay, so now the corpus increases. If you look at the vocabulary, it increases. Okay, if you try to transform, you will be getting the sentence result as well, like this. So that's how this works. If you fit and transform, you can see now we have for this sentence and the next sentence and so on. That's how we fit and turn them into numbers. And as we can see here, it is not a great way of doing it. Okay, anyway, I hope we earlier had our data variable practice sentence. First let us try to fit it. So bag of words dot fit data. Okay, so now we have fitted, right? If you try to transform in this entire thing, so if you have a new word, transform, and let me pass a word which is, here we have Loki, right? So I'll pass Loki as Loki has bought a iPhone or Amazon product. Okay, so we turn them into array. Usually you will be turning them into array, so you get numbers, so we will be training our model with it. That's what the entire idea will be later on. So this is the corpus which we get when you try to turn them into array as well. So moving into the next one now. So this is bag of words, they have some limitation. So moving into the next one, which is the TF-IDF. So practical data, when we do look into the project in the next session, we will imply all these things practically with the proper data set. And term frequency infers document frequency, also called as TF-IDF. So TF-IDF is a technique used in NLP to reflect the importance of a term in a document. Here it is just getting that. Okay, some advanced version is TF-IDF. It measures of how frequently a term appears in the document, as well as it is also going to measure the inverse document frequency. It is a measure of how rare or common a term is across the entire corpus. For example, the TF-IDF is a calculation actually. So if you look into that, it does two things actually: term frequency and then inverse document frequency. You calculate it and finally multiply it. So what is this term frequency? We'll see what is inverse document frequency and how to calculate it we see, and then finally we understand this. So term frequency, it is a measure of how frequently a term T appears in a document, and N is the number of times the term appears. Like for example, here the formula is, if you have a word, you are going to count how many times it occur, okay, in the document D, and then divided by number of terms in that document. So if you calculate it, you will be getting the term frequency. Here N is the number of times the term T appears in the document D, and each document and term will be having its own TF value. So when you calculate this, for example, simply I'll tell you this review 2, like this movie is not scary and is slow. Here the vocabulary we have is 8 words, and the term frequency for the word this is, the word this here appears only one time, so it is 1 number of times is appear in that sentence divided by the entire vocabulary, which is 8. So 1 divided by 8 is for this sentence. So like that, if you look at here, you have a table for review 1, for review 2 and review 3. This is their appearance, whether they have or not 1 or 0 and how many times, like our bag of word. And when you imply term frequency, out of the total 7 words in review 1 time this word has occurred, that's 1 by 7. Okay, so like that we get, if you don't have, you will be having 0 here. See here, and see here you had 2 times, so it's 2 divided by 8 is 1 by 4. So like that they give a fraction, that's term frequency. And we also have inverse document frequency, and inverse document frequency is a measure of how important a term is. So we need to we need the IDF value, because computing just the TF is not sufficient to understand the importance of word. In that, for each sentence we are getting different TF, right? This IDF is for entire corpus, so we understand how important it is by calculating log of number of document divided by number of documents with that term. Maybe if you have a sentence, what's the total number of document divided by number of document having that particular term. If you look at this log of this formula, if you check for the word this, it's appearing in all 3. So number of document you have or number of sentences is 3, number of document which has that this is 3, so log of 1 will be 0, and like that you can calculate the IDF value as well. So after calculating both, we need to just multiply them. So the final TF IDF for each is these values. So it's not just 0 or 1 representation. Here you get how important it is based on the values we get here. And the higher the value, which tells that to more importance it is, and lower the value, less importance it is. So we can actually use this with the help of feature extraction.text. We can use TF-IDF vectorizer. So let us first imply this in the Google Colab. And before going down, maybe we can fit and transform this as a 2D. Okay, so we'll do that later. So while going into our TF-IDF, from sklearn dot feature extraction dot text, let us import TF-IDF vectorizer. Okay, not transformer, vectorizer. So TF is equal to, we need to create an object. So TF-IDF is equal to TF-IDF vectorizer. Fine. So now we have it. We can call TF-IDF dot fit data inside. So the fitting has been happened now. If you want, you can once again look into TF-IDF dot. You have all the options like vocabulary underscore. So you get their numbers exactly. So what it is, and what we can also do is we can, this is their count corpus, and if you want, you can go with TF-IDF dot transform. Let us pass some sentences. Loki as, so you have to let us have it turn them into array as well. So for these, each word you will be getting 2Ds, because this is for the word Loki, you have one there, and for these words you are having them. So the TF-IDF is calculated, and finally you will be getting, which is different, right? So if you imply this same thing, if you are with your bag of words, let us call bag of words dot transform and pass this to array, you get it differently. Okay, so you get their presence, a 1 and 0, and here they give the importance as well, whether it is importance or not. So that's the difference between the bag of words and the TF-IDF as well here. So if you want to know for each word how important it is, we can also do one more thing from the TF-IDF. For example, you can get TF-IDF dot get feature underscore names out. This can be done with bag of words as well. You will be getting a list of all your corpus. So I'll use for T in this get one by one, and I'll create a temporary variable. You can call TF-IDF vocabulary underscore, because we need to get what exact position it holds. So we'll be getting a position of it, index, right? So I'll print T comma and then separate it with colon, and then I'll call TF-IDF has something known as IDF underscore. So it calculates and gives you the exact value. So if you do this, you will get the value for every one which you have in your sentence, the IDF value. So this is a thing which you can also do. So the final topic of this session, which is n-grams. So what does this n-grams is? N-grams, actually till now we have done the basic preprocessing. TF-IDF compared with bag of words will do better, and lot of deep learning or machine learning projects still work with TF-IDF, which is good. There are some very advanced version which is like word to vec and all, which we'll see later after deep learning. With this we can comfortably do projects, but still there is a problem is the combination of words mean something, right? Here we have the meaning you are transferring, but still how one word is related, not good, not long. So this not is present, but we don't know whether it is telling the longness or slowness or about the movie. So for that we need combinations to be understand. That's where n-grams come into play. So n-grams are continuous sequence of words or symbols or tokens in a document, and in technical terms they can be related as the neighboring sequence of items in a document. Maybe for example, we have n-grams, it is called because you can have 1 gram which is unigram or bigram or trigram and all. So the unigram of this sentence is I, comma reside, comma in, comma Bengaluru. If you go with bigram, then it is I reside in Bengaluru. So 2. 3. Trigram means I reside in Bengaluru. So it comes in combinations and it works, especially when you have something like this. For example, you can simply use it with our bag of words itself. Earlier we created bag of words, right? You can pass a n-gram range here. Okay, You maybe for example we pass it as 2 comma 2. I'll tell you what the range, how to mention it. So we'll fit it. Okay, we don't have array for fitting, so we fit it with n-gram range 2 comma 2. So if you look at bag of words dot vocabulary underscore, you get all the words, right? You will be getting, which is something like this, all the two combinations. But this is also a problem. You need to also have the single word and double word. That can be done if you go with 1 comma 2. So you get single word as well as their combination. So if you fit with this, especially now, and if you get the vocabulary underscore, you get hello everyone, this every separate thing and then their combination as well. Okay, if you look at this, if you want trigram, you can choose 1 comma 3 for triple combination, or 2 comma 3. If you want all the 2 and 3s, you get 1, then 2 and 3 as well. If you go with 3 comma 3, you get all the 3 combinations only. Hello everyone. Then this you will be getting triple combinations. So that's how we get. So once you have it, you can transform them as well, right? So the count increases. This can be done with TF-IDF as well. So we can pass the n-gram range is equal to, if you want 1 comma 3 will be good because you capture everything, right? So you get the, now the vocabulary is big. You can see if you transform this, you get a lot of details because you are now passing the combinations as well as a parameter or a different word. And if you look at this, now you get the values for their combinations as well. If you want to convert this masterclass into 1 month certified internship on natural language processing, you can join as an internship user, and you will be getting 30 days of recorded sessions, 30 days of PPTs for download, all the downloadables of every 30-day content, 10 plus source code of project files, 1 month internship certificate, participation certificate, 90 days of access to all the courses, 4 hackathon live session and community group. And you can get all these things at a discounted fee at $799, and the registration link is posted in chat box. You can join as an internship user and get all these benefits of 1 month internship. You will be getting 30 days different day-wise plan starting from the basics of machine learning with their project, and then the NLP continuation as well. So you can get all these things at a discounted fee at $799. The registration link is posted in chat box. And if you want to register for our 4-in-1 bundle offer, today is going to be the last date. So you can get Python with machine learning, with NLP, with generative AI, 4 different internship. So you can get or learn from the scratch. It is 4-in-1 bundle offer. The registration fee for it is $1,299. The offer ends today. Today is the last date for it, and the registration link is available in chat box. It's a limited offer, and this is going to be the last date. So if you get this, you will be getting 4 different certificates, 120 records, weekly live session, 30 plus projects, downloadable PPTs, internship confirmation letter, 1 year validity for using this, and community support. It's a self-paced course. You can watch at any time, and today is going to be the last day for availing this. So you can register for this 4-in-1 bundle offer by clicking at the link which is posted in chat box. So that's it, the basic pre-processing, and in the next session we'll see project support.